Welcome to the hands-on part of the tutorial. Before we proceed to the hands-on, a little bit of housekeeping first. First, if you haven't already, get the latest version of the notebook from either GitHub or this URL, which gives you a zip archive to download. The easiest way to run these notebooks is using IBM Quantum Experience. So for that, you can just go to quantum-computing.ibm.com and log in with your IBM ID. Then you can go to Jupyter and upload your notebook, the notebook that you've downloaded either from GitHub or from that zip archive. You can also run a notebook locally on your machine. All you need to do is install Qiskit. So you can also do that. That's what I'm going to do in this tutorial myself. So without further ado, let's just jump right in. As I said earlier, you can either run this on IBM Quantum Experience, which doesn't require installing anything, or you can run it on your own machine. And that's what I'm doing now. So if you want to run it on your own machine, you have to make sure that you have Qiskit installed. And for that, you just uncomment this line here and you run it. Or if you have an older version of Qiskit, you should update it. And the reason you should update it is because this only works on, or is only tested at any rate, and on this version of Qiskit 0.20.1. Because Qiskit is still not stable, it changes a lot from version to version, and there are a lot of breaking changes from version to version. Okay. Our motivating example, and the thing that we're going to be trying to do throughout this tutorial, is to solve maxcut on a simple graph. Recall that this is our the formula on top gives our maxcut objective. We're maximizing 1/2 sum over edges, 1 minus size j. First, we're going to drop all the constants because they do not affect the optimum. And so it just becomes sum over edges si is j. And as we remember, we can construct a Hamiltonian for it just by mapping the eigenvalue, the binary variables si onto the eigenvalues of z. So our Hamiltonian is sum over edges zi zj. So to solve this Hamiltonian using qaoa, we need to implement the following circuit. And the rightmost part is easy. So initial state 0 given, layer of Hadamard's easy. Now what we need to do is we need to implement those alternating operators, the cost of phase separation operator and mixer operator. So let's begin by importing all the things we're going to need. And let's consider this bipartite graph. Now note that this graph is, of course, trivial to solve because it's bipartite. The solution of maxcut on it is just take all the vertices in one part and put them in one part. So for example, 3 vertices on the left become part 1, and 3 vertices on the right, 2 vertices on the right become part -1. But everything we do on this trivial circuit, and all the techniques we're going to use on this trivial, graph, they all apply even for harder problems. So let's start by building the circuit for the cost operator. Our cost operator is exponent of minus I gamma c, where c is the cost Hamiltonian, which is the sum over edges zi zj. And we can do it by just applying gates. So what we're doing here is we're going through the edges. So we create the circuit, we're going through the edges, and for each edge we append zi zj term, because as you remember, they commute, so we just concatenate them. And the way we append them is we apply C naught, RZ, and C naught. And this gives us our cost operator circuit. And this is straightforwardly enough. And we can run it plug some angles and see what comes out. And we see that it's correct circuit. It's kind of hard to see here because the Qiskit, the circuit drawer, pushes gates as far to the left as it can. So you get these terms. So this, for example, is term corresponding to the edge 0, 3 in the graph. Then this corresponds to the 0, 4. Then this corresponds to 1, 3, and so on. The second thing we need to build is the circuit for the mixer operator, which similarly for each node we apply, which is the mixer operator is exponent of minus I beta b, where b is the sum over all nodes Pauli x's. What this is, because they all commute, it's just a product of corresponding exponents, which are simply rotation around x applied on each node. So the circuit is we go through the nodes, and for each node we append this Rx term, right, which is just Rx gate, just one gate. And we can draw it. Looks exactly like we want. And this really gives us the entire qaoa circuit. There's not much more left. So basically the way we get the full circuit is we start by applying a layer of Hadamards and then apply these p alternating operators by just appending the circuit to our appending corresponding circuits, alternating operator circuits to our circuit. Here at the end, I'm going to add the measurement. And this is something that we need to do if we want to use a shot-based simulator or sample-based simulator. If we want to use a state vector simulator, we don't need to measure, but we will get to it in a moment. And we can draw the entire circuit. We see exactly that. We have a layer of Hadamards, then we have these terms, each one corresponding to an edge. And then at the end, we see a layer of these rotations, Rx, that correspond to our mixer. And this is for p equals 1. And after all of this, at the very end, we measure. Okay, now we can run this circuit, this qaoa circuit. Note that here we're going to be running them in simulator. And let me go straight. Yeah. And to run them on IBM, on real IBM quantum computers, all you need to do is to change the backend. I'm going to show you how. However, keep in mind that these circuits get pretty deep. That is, they start to have a lot of gates pretty quickly. So with noise, you start having issues fairly quickly with real hardware noise, that is. Another thing to note here is that Qiskit uses an ordering where the 0th qubit is the rightmost or the least significant bit in the bit string, and your last qubit is the most significant bit in the bit string. So we need to invert all samples we get from Qiskit. And I added this little helper function for you to use. And so we're going to do just that. So we're going to take a backend. In this case, it's a QASM simulator. QASM simulator is a shot-based simulator or sample-based simulator. And then we execute our job and we get the results. And then finally, for the results we get, we have to invert all binary strings because they are in opposite order of what we expect. And we get just a bunch of binary strings out. By default, I think it's 1,000 binary strings that you get. Now, how good are those results, right? Because at the end of the day, we want to sample binary strings that are solutions to our optimization problem. To answer that question, we need to compute the value of what I call qaoa energy, or the expectation of the objective on these binary strings. And because our Hamiltonian is a classical Hamiltonian, we don't need to do any of the techniques that people use in VQE. We can just measure it directly from samples fully classically. And the way we do this is we just go to the binary string, and for each edge, we look at the corresponding bits are equal or not. And if they're not, the edge is cut. So for example, this binary string gives the optimal solution to our problem. Remember, it's a bipartite graph, so we put the first three nodes on the left in one part, in one partition, and the two nodes on the right in the other partition. And that gives us our maximum cut, which is 6. So keep this number in mind for later. Now we can compute the energy that we got from the sample. And the way we do this is we go through our count through the samples that we got. And for each sample, we compute the value and we multiply it by how many samples like this we've got. So if we have, 3 strings 0, 0, 0, 1, 1, 1, it's minus 6 times 3, and that adds to our energy. And then we just compute the expectation by dividing it by total number of counts. And so this can give us the energy that we got from running our circuit. And note again that we have to invert the counts because they're in opposite order of how the nodes are indexed in our graph, or how we index the bits in the binary string. With these built-in blocks, we can finally fully run qaoa. Remember that the way we view qaoa and the way we're going to run it here is we run it as a variational algorithm. So we need a classical optimizer to find the optimal parameters beta and gamma. Here we're going to use constraint optimization by linear approximation, or qaoa, from SciPy optimize. But we really can use any optimizer that we like. So all we need to do this is we need to wrap our circuit into a black box objective function that qaoa can optimize. And note once again that by convention, all optimizers perform minimization, and this is why we put a minus in front of our objective earlier. So this is our objective. So the way we get it is we get the backend, we build the circuit, we get the counts, and we compute the energy. Note that here I seeded, because simulator is classical simulator. So inside of it, the way it gets the samples is it has a pseudo-random number generator inside of it. So here, for pedagogical reasons, I fixed the seed to show you an effect that I'm going to talk about later. But this can also be good for reproducibility. If you run some experiments, in your paper or in your presentation, you can fix the seed for the simulator and you'll get the same samples every time. Okay, now let's finally solve the optimization problem. So we're setting here p equals 5. So we have 5 alternation operators. And once again, we start from an initial point that I chose for a reason that's going to become apparent soon. And we will limit our number of iterations to 2,500 here. But note that we terminate only after 134 iterations. So we didn't exhaust the budget. And we get a pretty good solution, right? Our energy in the end is 5.3. To get the actual solutions, we need to run the circuit again with optimal parameters. So we grab the optimal parameters, we plug them into our circuit, and then we execute it in the simulator. We get the samples, and then we invert them to get the correct order of bits. And this is our full sample. And we see here that the most frequent strings are the ones that correspond to the correct solution, to the true optimal solution, where first 3 nodes are in one part and the second 2 nodes are in the other part. And similarly, another frequent string is the same thing, but up to bit flip symmetry. So we can plot how good the results are, and we see the same thing indeed, that more than 70% of our results correspond to the true optimal solution, which has energy minus 6, or cut of 6. So this is pretty good. And we can even visualize the results. So we take our binary string and we color the nodes of the graph using the bits from this binary string. And indeed, lo and behold, this is our correct solution. Now, what if you want to get to run this simulation using the full QAOA state. You want to get the full QAOA state out. So you want to get all amplitudes. And Qiskit provides a state vector simulator backend for this. A state vector is simply a vector of amplitudes. So for example, this Bell state, which is 1 square root of 2, 0, 0 plus 1, 1, corresponds to the state vector of 1 square root of 2, 1, 0, 0, 1 square root of 2. And this is exactly that if we try running it. So we build a circuit, Hadamard on first qubit C0, and we execute it, and we use state vector simulator backend when we get as our backend. And then another thing we have to do is we have to do get state vector instead of get counts. And that gives us a NumPy array with all the amplitudes. Now, unfortunately, the qubit ordering issues are still there. And I added these tools here for you to use. I took them from this GitHub issue. And what they basically do is they invert the state vector. So if you have a state, you can get a state with the opposite ordering of bits, which is very convenient for us, because this is how we're going to get our energy correctly. But we can run QAOA using state vector simulator basically the same way as we did it with sample-based, shot-based simulator, QASM simulator earlier. First difference is we do not measure. So when we get the circuit for state vector, we do not add measurements in the end. It's just the gates. Because if we get them, if you do the measurements, then the result will collapse, and instead of full vector of amplitudes, we'll just get one non-zero amplitude, which is not what we want. And second thing we need to do is we need to know which amplitudes correspond to which computational basis states. And this is a little helper function that basically takes our state vector, which is a NumPy vector of amplitudes, and converts it into a list, into a dictionary, excuse me, that maps binary string to amplitude, similarly to our counts work. So first thing, how can we check that this is correct? We can just take the optimal parameters that we found with a shot-based simulator and plug them into our state vector simulator. So this is where we do it. We get the circuit, we plug the optimal theta here, and then we execute it on state vector backend. We get state vector, and we get adjusted state. So we flip the order. And this is our amplitudes. And we drop, another thing we do here is we drop ones that are too small, that are under the epsilon, some epsilon value. Though in this example, there are none. All of them are non-trivial. And so the states that have the largest amplitudes, as you can see here, this is the first one that has, nope, my apologies. This is the one, yeah, 0.6. And the other one is this one with large amplitude, same amplitude. No, they're going to have all the same amplitude because QAOA state preserves the Z2 symmetry. And we can compute the energy and we get out the same number, which at least tells us that we implemented the simulator correctly. And this computes this little function computes the energy for a state vector result for a full state. And now, by just converting to a black box objective, same as before, we can run the full optimization loop with the state vector simulator. And this is going to take a little while. And the reason it's going to take a little while is you'll see in a moment we're going to saturate this limit. We're going to get to this, we're going to hit the maximum number of iterations, which is 2,500. And note here that I'm starting from the same initial point as the shot-based or QASM simulator. So they are comparable directly. You would expect the two simulators to get to the same point, right? Because we're using the same simulator, which is Kabbalah, and we're starting them, which is Kabbalah, it's a deterministic simulator. There is no randomness there. And then we're starting them from the same initial point. With the magic of editing, we can cut straight to where it finished. And what we note is that we get a much better function value. We get minus 5.946, which is almost 6, very close to 6. And actually, you can try this at home, but we can get, in fact, if we run this long enough, we get a solution that's arbitrarily close to the true ground state, to the minus 6. And you can just try plugging in maxiter 10,000 here and run it, and you'll get 5,99999. The longer you run it, the closer you'll get. And this is interesting, right? Because we're running the same simulator. We are in the same optimizer, different simulators, but they're simulating the same circuits. And they get into different points. Whereas with samples, with shots, we only get to 5.3. Whereas with full state, we get to 5.95. So within 0.05 of the true optimum. It's a big difference in optimality gap. And the reason it happens is because we get stuck in a lower quality point. So if we look at the points where the one optimizer gets stuck, it's pretty far away from the point found by the optimizer that uses a full state to estimate energy. There are two distinctly different points. Now, an important point to make is that this is not a local minimum. So if we just take the same initial point that the QASM simulator, the Kabbalah with QASM simulator got stuck in, and we plug it into an optimizer that uses full state vector objective, and we run it for just a few steps. And we also make sure that we only work in a small neighborhood of this point. So we set this initial perturbation that Kabbalah uses to be a very small number. And even just in this neighborhood, we already get a better point. We get minus 5.38 roughly. So we get 0.08 improvement in just a couple of steps from this point. And know that it's very close to it. So if you compare this point to the point we've seen before, you'll see that they're very close. So just in the immediate neighborhood of that point, there are better, higher quality points. And the reason for this behavior is that deterministic optimizers like Kabbalah assume that every function value they get is true. And what it causes them to think that a point that they've sampled is a local minimum, when in fact it is not. So what we have to do is we have to bake this assumption of stochasticity, this understanding we have that the function that we're sampling is not determinate and is not true always. It's true only up to some epsilon. And without this assumption of stochasticity, we're going to keep having this bad performances. Okay, so that is how we run QAOA. And it's been pretty involved, right? But what we did here is for pedagogical reasons, we basically re-implemented the whole stack of tools used in Qiskit. And note that this is not really Qiskit specific outside of the qubit ordering shenanigans. It's fairly generic. You can do the same thing. All you need to do is to implement gates. You can do the same thing in Circ, PyQual, what have you, Q#. But in practice, you don't have to re-implement QAOA every time you want to use it. Instead, you can just use tools that your favorite library, be it Qiskit, be it Circ, be it PyQual, provides. So let me walk you through some of the tools that Qiskit provides for you and how they match I'll show you how they match exactly what we've done so far. So remember our pipeline, right? We start with a problem class and a problem instance, which is a maxcut and a graph instance for a maxcut. We come up with a general Hamiltonian for this problem class with pencil and paper and using the Feynman method of sitting down and thinking hard. Then we build specific Hamiltonian for this problem instance. And from the Hamiltonian, we can construct the QAOA circuit. Then we take the circuit, we wrap it into a black box objective function. We use a classical optimizer to find good beta and gamma parameters. And finally, we get the solution by running QAOA with optimal parameters. So first, let me show you how Qiskit can help you with building the Hamiltonian. So these two steps 3 and 4, can be done by Qiskit for us. Oops. Yeah. So this is the function I copied and pasted from Qiskit. But basically what it does exactly what we've done earlier, except it uses the adjacency matrix of a graph. But it's the same thing. This is just a loop over the edges. And for each edge, we insert zi, zj term, and they're represented as Pauli strings in a form that is basically stabilizer form, if you're familiar. And then our operator is just this list of Pauli operators, complemented by a shift to make sure that the eigenvalues of this operator minus shift, or in this case, plus shift, eigenvalues of this operator plus shift are exactly the energy levels of the original problem, of the max cut problem. So recall that our objective is sum over edges zij. Our Hamiltonian is sum over edges zij. And this is exactly the Hamiltonian that Qiskit builds for us. So it has 6 terms for each edge. So this term is for edge 1, 4. This term is for edge 1, 3. This edge is for term, excuse me, the opposite order. Recall that they are all ordered in opposite order. So this is 0, 3. This is 1, 3. This is 2, 3. This is 1, 4. This is, 0, 4, 1, 4, and 2, 4. And it's exactly our Hamiltonian. How can we know that our Hamiltonian is correct if it's a larger Hamiltonian, right? We cannot just examine it manually. And as you recall, Hamiltonian is just a matrix, really, for our classical problems. So all we need to do to find its ground state is we need to find its largest eigenvalue, eigenvector, or smallest, depending on which way we're going. And for that, we can just use an eigensolver. And Qiskit provides us a NumPy eigensolver that wraps around its Pauli operator objects. But all it is it uses inside of it NumPy linealg.eig. And we can call it on our Hamiltonian, and we pass k equals 1 means lowest eigenvalue, which is the ground state. And we get our eigenvalues and we get our eigenstates. Now this is a little difficult to read, right, because we get the full state vector. We get the full eigenvector, which is 2 to the power of 6 long. So Qiskit provides us a convenience function for this, which is sample most likely. It basically converts the eigenvector, which is a state vector of the same size as state vector, to a binary string. And it takes the one with the largest amplitude. And if we run it on our output of the exact eigensolver, we get the correct solution, which is 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, with first 3 nodes in first part and next 2 nodes in the other part. And the cut is -6, as we expected. So we build a Hamiltonian correctly. Now you can, of course, use the same process. You build a Hamiltonian, then you run exact eigensolver on it. In prototyping, if you want to build a Hamiltonian for your problem, you can start by building it from Pauli strings and then just running eigensolver on it to make sure that it's correct. Note that you can also build your Hamiltonian simply as a matrix in NumPy. Right, so remember that your Hamiltonian is sum over edges zi, zj. So if you have I, which is identity matrix, and z, which is diagonal 1 minus 1, you can just combine them and tensor product them together in NumPy. And you'll get an operator. You gotta have to do a lot of numpy.cronker product, but you get the same result. You can actually verify that as the same result by plugging them into np.linealg.eig, which is eigensolver, get the lowest eigenvalue, and plug it into the convenience function that converts it into solutions, which is 1, 1, 0, 0, 0. And you get the correct solution and you get the correct value, which is nice. You can also do that. The issue is, of course, this full thing is a very large matrix. You cannot, if you construct it explicitly, it's going to be horribly, horribly slow. So that's a reason not to do it. But you can, and it's helpful to verify that you're doing everything correctly. Now, the beauty of Qiskit is that it can also build the, now that we have the separator, it can also build a QAA circuit for us. And the abstraction it uses is a variational form, which is just a parameterized circuit that prepares a parameterized state. There are many variational forms in Qiskit. QAA is just one of them. And so this modularity of it allows you to just take this variational form and plug it into any algorithm inside the Qiskit that you want. So let's run this circuit and note that we add a measurement here because the Qiskit variational form does not have a measurement in it. When we run it on our backend, we get out some counts, exactly the same as we ran our circuit that we've constructed ourselves. Except that we have to call this construct circuit method instead of, in our function, we had a get QAA circuit method. But it's exactly the same thing. We just re-implemented it ourselves earlier. And we can compare that it's the same as ours. So if we look at our circuit, it's layer of Hadamard's, then controlled not, RZ controlled not for each edge in the graph. And then in the end, it's Rx on each node. And if we look at the, let me hide this. If we look at the Qiskit circuit, it's exactly the same thing if we transpile it into the same gate set. It's a layer of Hadamard's, and then C0, RZ, C0. It puts them in different order, but it's the same gates, actually in inverted order. And then a layer of rotations around X on each node. The two match. In fact, we can confirm that the two circuits produce the same unitary. And of course, they're going to produce the same unitary up to global phase. Make sure that we can take care of that too. And we also want to get rid of small numerical errors. So if a unitary has 0, sometimes you get this weird numerical issues where you have tiny values in your matrix, so you want to filter those out as well. And then by plugging into a unitary simulator, which is a Qiskit simulator that gives you the full to the power of n by 2 to the power of n unitary realized by the circuit. We can get this unitary for our circuit, for Qiskit circuit, and they are equal. Make sure that they are equal. You might wonder, can I use the Hamiltonian that I've built in NumPy earlier? Yes, you can. So all you need to do is to convert it into a matrix operator, which Qiskit provides, and then you can plug it into QAA variational form, do whatever you want with it. The issue is it's going to be slow, so don't do it. And actually, if we run it, I think here, you see that it gives us a bunch of warnings telling us, don't do this, it's going to be slow. And this is the highest level of abstraction that you can do in Qiskit. So instead of doing all the things we've been doing here for a bit, you can just import optimizer, import QAA algorithm, and you plug in your Hamiltonian. You get a simulator that you like, and then you just run it, and out comes the solution to your problem. Now, the challenge with these kind of high level of abstraction interfaces is that it's often hard to know what goes wrong. For example, that issue of state vector versus chasm simulator is probably very difficult to detect if you're just using these high-level objects. Or for example, if your circuit is too deep and you try to plug in it and run it on hardware, and you get out the results that gibberish, or it takes a million years to run. It's hard to debug which part in particular breaks. And so it's nice to do it from the ground up if you're a researcher, or even if you're a practitioner. With this concludes our hands-on part of the tutorial. And I'll see you in the Q&A.